This is a conversation with Sheldon Goldstein. He's a theoretical physicist and a distinguished professor of mathematics, physics, and philosophy at Rutgers University. In this conversation, we discuss quantum mechanics, the Copenhagen Interpretation, why did it become so popular, what are the big problems with it. We talk about the measurement problem and randomness, and then we spend the bulk of our time talking about pilot wave theory or Bohmian Mechanics or the de Broglie-Bohm theory. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, or rate 5 stars in Apple Podcasts. This project takes a lot of my time, money, and efforts. If you'd like to see it continue, do consider making a donation on Patreon or Anchor. You can buy super thanks on YouTube. You can leave a gift on Instagram Reels. If not through monetary channels, and do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For the forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now it's no time. I want to start with the same question that I asked Tim Maudlin when he came on the show earlier in the year. In the book, New Perspectives in Physics, Louis de Broglie said the following words: "Science itself, no matter whether it is the search for truth or merely the need to gain control over the external world, to alleviate suffering or to prolong life, is ultimately a matter of feeling, or rather, or desire. The desire to know or the desire to realize." So let's start here. What desire does science and physics satisfy in your life? When you look back on your life, why did you gravitate towards science and physics in the first place? What feeling were you chasing? Was it the search for truth, the need to alleviate suffering or prolong life, just like in the words of de Broglie? Or do you think there's an even deeper purpose to the work you do? There's another reason for why you gravitated towards physics in the first place?
Well, in my case, it was an aspect of the search for truth, but not just any truth, but really what lies behind what's going on in our world. What explains what we see around us? Well, there are lots of kinds of truth. There are philosophical truths, mathematical truths. What interested me were scientific truths. I might say truths of physics, but at the time, I was really young when I realized that I really liked science, because I enjoyed the kind of understanding I got from it, how things work. It wasn't so much that you could calculate things. That's pretty important for the use of science, both for good and for bad. But that wasn't really what intrigued me. It was the understanding which science affords. What's in the world? How does it behave? And that's particularly satisfying with how things behave has a certain compelling aspect to it, a certain simplicity, a certain aesthetic beauty. When I was young, and that's me 6, 7, 8, I don't know, 9, I wasn't thinking in terms of physics. I didn't know what physics was. I was, however, intrigued by atoms. I think I learned about atoms from maybe some Walt Disney show on television, something called My Friend the Atom. Before that, I don't think I knew anything about science. But as soon as I saw that, I knew I liked science. And as soon as I learned what physics was, I realized, oh, that's the kind of science I really like most. So that's how I got started, very young age. And I pretty much stayed that way. Same. What motivated me then is what motivates me now.
Would you say your love for physics? It's interesting that you say that your love for physics has stayed the same after all these years, after everything you've done. Are you saying that pure love that you have for physics that started with my friend Atom, that Disney show, has stayed consistent? Has it not evolved over the last few decades?
No, the basic feeling has not changed. Of course, my understanding has changed, but not the basic feeling, not my sense of what physics is about. Now, it is true that many people, after studying physics, particularly generations ago, I may say 2 or 3 generations ago, after studying physics, their idea of what physics is about often changed into something much more practical, into understanding not what the world is made of. That became unfashionable. Rather, just how to make predictions about results of experiments, or how to devise something very practical and practically oriented. That was probably a consequence of the way quantum mechanics was taught.
Yeah.
Anyways, I don't think that ever deeply affected my understanding of what physics should be about.
The biggest driving force for you was the search for truth and to understand how the world works. How challenging has it been for you to stay committed to this quest for the search for truth, even if that means pushing against some of the most conventional theories of our time, some of the more popular theories of our time? You've said in the past about the de Broglie-Bohm theory that there was a time when you couldn't even talk about it because it was heretical. It probably still is the kiss of death for a physics career to be actually working on Bohm, but maybe that's changing. And it's interesting because to an outsider like me, science seems to, or physics in particular, seems to be very strongly divided into this group that swears by the Copenhagen interpretation, just like there's a group that swears by string theory. And if you're not in that group, if you don't toe the line, if you don't repeat the official narrative, you're often shunned aside. Like you said, it's considered heresy to a certain extent. It could be the death of a physics career. Has it been challenging for you to push for the search for the truth, given this current context, even if it means pushing against these popularly accepted theories like the Copenhagen interpretation?
Oh, I think I was pretty lucky in the sense that I never was in a situation where I had the feeling that my job depended on avoiding the questions I was interested in.
Yeah.
That was partly because maybe I've been in a math department just about my whole career. I think my whole career, just about. Yeah. And most of my earlier professional work was in mathematical physics. And so my advancement did not really require towing the party line about quantum mechanics. So maybe I was lucky in that way. I know quite a few younger people who really do want to engage and understand and work on foundations of quantum mechanics. This can be rather tricky for their career, as you said. And I often will discourage them because it's their career. They have to first get a career. I think the situation is still not entirely healthy.
What advice would you give to people in that case? If you mentioned you were lucky, I don't think every person can walk into physics through the mathematical department. So what is the way to actually break this vicious cycle? How to make it healthy again? Because it seems like if you want to build a physics career, you have to start towing the party line, but then you've already lost yourself.
I don't know. I wish I could tell you I had some great advice. I guess what I often tell people is either you go into mathematical physics or something else, or go into regular physics, get tenure, and then do what you want. Or go into philosophy of physics, and then you could do what you want right away. But I think it's going to be very risky to go into physics and start working on issues and foundations of quantum mechanics to get tenure. I may be wrong, but I don't think the situation has changed that much. I know some people may be more optimistic than me, and they may be right. But
well, uplifting to hear. Okay, let's dive into the physics itself and let's try to break it down. So I think to set the context for everything we're going to talk about, to set the foundations properly, I think it'd be helpful if we can have a quick introduction to quantum mechanics. So I'm going to ask you a very simple question. What is quantum mechanics? What is the Copenhagen interpretation of quantum mechanics?
Well, here's the problem. It's not clear what the Copenhagen interpretation is.
Yeah.
It would be very nice if there was some very clear thing. You would say, here's what it is, and here are its difficulties. Part of the difficulty in talking about its difficulties is you don't know what it is. I don't think any two physicists agree on what the Copenhagen interpretation really is. There was the rules of textbook quantum theory. There was that. And you can add on to those rules some quantum philosophy associated with Niels Bohr.
Mm-hmm.
Does the Copenhagen interpretation include that philosophy? Well, maybe if you're talking about what most physicists believe, and I would say most still would say they adhere to the Copenhagen interpretation, they don't understand Bohr's philosophy. That's not what they're talking about. They're talking about the usual rules they learn and some rough and ready principles that go along with those rules to avoid embarrassing questions. One of those rough and ready principles might be shut up and calculate, which I think might be healthy in some respects, but really is quite opposite of my understanding of what physics should involve. Calculation is important, but you shouldn't shut up. You should try to understand the calculations, and you should understand what your theory you're working with, be it plausible or implausible, actually says. And it's not clear what the Copenhagen interpretation says, even textbook quantum theory. Why is textbook quantum theory obscure, even without the philosophy? There are a whole bunch of measurement axioms, rules for what happens in measurement. And part of the problem with that is that once you begin to understand those rules, it should be clear to you, but it probably doesn't become clear enough, that whatever you have in mind when you're talking about measurement, it's not really measurement. Because one of the things you learn is that until you look, quantities which you are measuring don't have values. Well, if they typically don't have values before you look, then you're not measuring anything. You're not measuring means finding out what's there. If there's not something there, you're not measuring. So it's not clear what those axioms involving measurement are actually describing, because they're not describing genuine measurement. Now, that's one example of the vagueness. What else is vague? What's fundamentally real in quantum mechanics? Totally obscure. There's very little commitment. If you take a whole course and almost go through your graduate school in quantum mechanics, you're studying courses in quantum mechanics, quantum field theory, all kinds of stuff. It will probably not be entirely clear to you what is real in a quantum universe. What is quantum mechanics fundamentally about? You can't. And how can you say you actually understand the theory if you don't know what it's fundamentally about?
Can I ask you to just step back for a minute and then define what is textbook quantum? I take your point about that there is no agreement or consensus around what is the Copenhagen interpretation, but what is currently the textbook quantum theory? What are we measuring? What is the wave function? That will be helpful to introduce these concepts, because then we would be covering them when we talk about pilot wave theory as well.
Well, the question of what is the wave function is not exactly something you actually learn. A key ingredient in textbook quantum theory is that a system is described by its wave function. It has a wave function. And that wave function is a pretty abstract object.
Mm-hmm.
This gets difficult for somebody who doesn't know a little bit of quantum mechanics to begin with. What kind of object is the wave function? Well, it's a function on a fairly abstract space. It's only in very simple cases that the wave function of a system is reasonably simple. And even there, it's not that simple. For example, in textbook quantum theory, the wave function of a single particle is a function, complex valued function, but a function on physical space, three-dimensional space. That's just for a single particle. And without spin, it's a bit more complicated, this wave function, even for a single particle, if the particle has spin. I'm not going to get into that. And if you're talking about two particles, the wave function is a function of the positions of both particles, which means it's a function not on physical space, but on a higher dimensional space, really. If there are two particles in three-dimensional space, it will be a six-dimensional space. And for any decent-sized system of a large number of particles, it's going to be a very high-dimensional space. And one of the things you learned is that really is the state of the system, which means that's a complete description of the system. There are no further facts about the system than what is conveyed by the wave function. That is a striking statement, although it probably sails under the radar for most students. So, for example, for a single particle system, particle in space, the wave function does not tell you what the position of the particle is. So the particle doesn't actually have there's no fact of the matter as to the position of the particle, which is to say the particle doesn't have a position. Yeah. It just has a wave function. And then there's a famous evolution equation for this wave function, a very nice equation, one of the fundamental equations in quantum mechanics called Schrodinger's equation. Mm-hmm. Very nice equation. Mathematically, it's well understood. Schrodinger's equation. But while it's mathematically understood, so you know how the wave function changes with time, how the wave function is connected to physical reality is obscure. That's why you have in textbook quantum theory more than just the evolution law for the wave function, Schrodinger's equation. Because if you just had Schrodinger's equation, you would have trouble understanding where the predictions come from. There is one version of quantum mechanics where you do just have Schrodinger's equation, and then you do a lot of analysis to extract predictions. That's the many worlds interpretation. That is not textbook quantum theory. In textbook quantum theory, you have a whole bunch of further axioms, rules, in addition to just the evolution law. The first rule, which says you have a wave function evolving according to Schrodinger's equation, and you're told it's the complete description of a system. Then you have measurement axioms, which tells you, it's supposed to tell you what happens when you perform measurements, which are not really measurements. So I should better say, if I want to be more accurate, which tell you what happens when you perform certain experiments on a quantum system. And it gives you rules for the probability distribution of the result of that experiment. What experiment exactly is a bit obscure, because it's not clear, because they're not really measurements. So that's a whole story. Experimentalists know what experiments to do, but it's never conveyed very clearly in a quantum mechanics course or in a textbook on quantum mechanics. Although Landau and Lipschitz, I think, do a decent job. That's a famous textbook. So you learn how to calculate all kinds of things in a standard course, but it should not be at all clear to you what it is exactly that you are calculating. So that makes it a little difficult to be a quantum mechanics student, and that's why it's probably just good advice to the poor student to just shut up and calculate. Learn how to do the calculations. Don't worry about what it all means. Good advice, because you're not going to get what it all means if it's a standard text on quantum mechanics or a standard course. Better not to ask.
Yeah, your colleague Richard Feynman had said nobody really understands quantum mechanics. I guess it was more of a comment about how vague and incoherent it's got. Okay, you brought up a lot of limitations of textbook quantum theory at the moment, and I definitely want to linger on them and break them apart a bit more. Currently, there's this wave function that defines particles, which is, like you mentioned, this abstract complex value function. And you mentioned something interesting around how the wave function connects to physical reality is quite obscure at the moment. Albert Einstein, I'm sure the name rings a bell to you, once said about quantum theory that this theory reminds me a little of the system of delusions of an exceedingly intelligent paranoid, concocted of incoherent elements of thoughts. And then in a paper titled, Can Quantum Mechanical Description of Physical Reality Be Considered Complete, known popularly as the EPR paper, he went on to say, whatever the meaning assigned to the term complete, the following requirement for a complete theory seems to be a necessary one. Every element of the physical reality must have a counterpart in the physical theory. We shall call this the condition of completeness. Can you expand on this further? Why is it important to have this physical counterpart? Have this counterpart in a physical theory? Why is this such a big problem? And for that reason, why is Einstein considering the Copenhagen interpretation incomplete?
Well, no theory can explain everything, but if you have your theory and you're saying it is the final theory, then it better encompass everything in physical reality. It does. If it leaves something out, then you need a further theory to take care of what's left out.
Yeah.
Now, the founders of quantum mechanics were not suggesting, when they say the wave function is the complete description, they were not allowing for something to be left out. They're not saying, oh, we would need a further theory. Quantum theory is only some provisional thing which describes only a limited aspect of reality. That would be a reasonable thing to say. But even if it were something which described only a limited domain, it ought to say, describe everything in that domain. If it describes atoms, or particles, it ought to describe all aspects of the particles. So Einstein simply pointed out that it turns out that quantum theory, in talking about a quantum mechanical system, there are physical features of that system which are not captured by the wave function. So that the wave function is not, contrary to what is so often said, that the wave function is a complete description of the system. Einstein argued that it can't be a complete description of the system. There are things that are left out. And if their wave function is in fact not a complete description, then you should do better and actually include the things that are left out in that description. That might help you understand what your theory is about, after all. It was the incompleteness of the wave. The wave function description is so incomplete that it leaves out any coherent answer, at least from my point of view, to what the theory could be about. Suppose you have a theory about particles, for example. It's supposed to be about particles, but you leave out the particles. That's that's leaving out a lot, like the whole story. That's what Einstein had in mind. So incompleteness was a very serious flaw. It means saying the theory is incomplete. If you concede that your theory is incomplete, that means you have more work to do. That's why quantum physicists wanted to resist the idea that their theory was incomplete. They wanted to use the theory to get more and more predictions using that theory, and not have to go back to the drawing boards to get a better theory, which completeness would seem to demand. Which incompleteness would seem to demand.
Yeah. You mentioned Schrodinger's equation, and you also mentioned the uncertainty around the position of the particle. So I want to also linger on this aspect of textbook quantum theory as well. Let's stick with Einstein. He had written a letter to Max Born in 1926, where he had said, quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but it does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he is not playing at dice. I want to linger on this last sentence, and let's talk about the role of probability and randomness and determinism. Is Einstein closing the door on any fundamental theory that involves any form of randomness or probability? Is it possible that maybe quantum mechanics or the textbook quantum theory is not a complete system? It's incomplete at the moment. Maybe it's a system of delusions, like you said, but it's not necessary that a fundamental theory will be deterministic, that there might be some probability or randomness involved in the fundamental theory.
I can't say, how committed Einstein was to the demand that a theory be deterministic, that it not involve fundamental randomness. Pauli commented on Einstein to Born that Einstein never really so strongly demanded determinism. He may have said that in 1927. It's kind of a nice thing to say, but Pauli said that was never a great concern of Einstein.
Yeah.
In any case, when I was younger, I actually very much liked the idea that there was randomness in quantum mechanics. I found that kind of exciting, and I was very much very happy to learn about the no hidden variable theorems, which, to me at least, in my ignorant state, said that, yes, quantum randomness, Einstein was wrong, and quantum randomness cannot be avoided. I really loved that. And it was only much later that I realized, a bit later, I mean, maybe sometime in graduate school, I'm not quite sure when, that I realized those no hidden variable theorems don't really prove what they claim to prove.
Right.
In any case, my lack of satisfaction with quantum mechanics was not because of its randomness. Randomness was never a problem for me. Whether it should have been a problem or should be a problem, I don't know. If somebody says I can't accept fundamental randomness, I can say, okay, I can understand why you say that, but I'm not sure I agree. If somebody says I can't accept that there's fundamental reality and that the observer must be always taken into account, I would have to say I really find it hard to believe you can think that. So this observer-dependent reality I've always found implausible. Although I once may have found it nice, exciting, and romantic, but I mean, very quickly found it implausible. After all, there is evolution. A lot was going on before there were observers, so I don't see how any serious physicist can take that seriously, that the observer is essential for physical reality, that the observer creates reality. Now, that's not plausible. But that there's fundamental randomness, I can't say that that's implausible, although I can appreciate that some people think it implausible.
So it is plausible that he is playing with dice. We don't know yet, but there could be a fundamental theory where there is randomness and probability. You brought up the observer. This has been your biggest gripe with it. So let's talk about it. At a conference in 2013, Quantum Theory Without Observers, you started your talk with this quote from Speakable and Unspeakable in Quantum Mechanics by John Bell. In fact, you've started multiple talks of yours with this same quote. So I'm going to read it out. A final moral concerns terminology. Why did such serious people take so seriously axioms which now seem so arbitrary? I suspect that they were misled by the pernicious misuse of the word measurement in contemporary theory. This word very strongly suggests the ascertaining of some pre-existing property of something, any instrument involved playing a purely passive role. Quantum experiments are just not like that, as we learned especially from Bohr. The results have to be regarded as a joint product of system and apparatus, the complete experimental setup. But the misuse of the word measurement makes it easy to forget this and then to expect that the results of measurement should obey some simple logic in which the apparatus is not mentioned. The resulting difficulties soon show that any such logic is not ordinary logic. It is my impression that the whole vast subject of quantum logic has arisen in this way from the misuse of a word. I'm convinced that the word measurement has now been so abused that the field would be significantly advanced by the banning of its use altogether in favor of the word experiment. So let's talk about the measurement problem in quantum theory. Why is it such a big problem? Why is the entanglement of the observer such a big deal? Why does John Bell propose banning the word measurement altogether?
Well, it's not that measurement is such a big problem. It's that the use of the word measurement is a problem when that word is inappropriate. Mm-hmm. If you think the word, if you misuse a word, you can get yourself confused. That word is misused all the time. That's a source of a great amount, if not most of the confusion in foundations of quantum mechanics. Don't abuse language. This is true in ordinary life, and it's true in spades in mathematics, and it's certainly true in physics as well. Don't abuse language. It's hard enough to think straight when you use language in a careful way. Yeah. If you're going to use language in a careless way, you're going to go off the rails pretty quickly. That was Bell's complaint. And then the proof that Bell was right is all the nonsense that people have said about quantum mechanics. From the abuse of a word, from the misuse of a word. Measurement doesn't really mean measurement. Observable doesn't really mean observable in the usual sense of the word. And yet you speak about a measurement and observables as if they were the familiar kinds of things we have in classical mechanics. It's not like that. It would be very good if quantum mechanics could be taught in such a way that just textbook quantum theory, but in such a way that language isn't constantly being abused.
I guess I'm still not clear on why or how measurement, the word measurement, is being abused and what problems it's causing in quantum theory. Why is it such a big deal that the word measurement is being used and the observer is such an integral part of quantum theory?
Well, think about the no hidden variable theorems. You get into all kinds of contradictions there. Some physicists have argued that these no hidden variable theorems and the contradictions you get to prove that there's no reality until you look. But they prove no such thing. All they prove is you really weren't, what you were doing were not measurements. You were just doing certain experiments. If in these theorems, arguments, you replace the word measurement by the word experiment, you would draw no such conclusions, no striking conclusions, and the contradictions would go away. What the no hidden variable theorems actually show are what are called quantum observables, which in the mathematics of quantum mechanics are associated with what are called certain abstract objects called self-adjoint operators on Hilbert space. And only students of quantum mechanics or mathematics might know what I'm talking about. But there are certain abstract objects. And if they're called the observables. What the no hidden variable theorems show is that there's no decent way to associate these observables with values in a manner which would agree with the predictions of quantum mechanics if in what are called quantum measurement, you were just revealing those values. That's what leads to all the contradictions. That's what leads to the conclusion that measurement must create reality. Well, if measurement were measurement, maybe it would have to be creating reality. Although that itself would be a contradiction, since if it's creating reality, it's not measurement anyway. But if these were not measurements, but were really experiments, there'd be no need to talk about anything creating reality. So the no hidden variable theorems in quantum mechanics, which have had an inimical role, are all based on the misuse of the word measurement. That's one good reason to avoid misusing that word. If you want to understand what's going on in quantum mechanics, you will have a lot of enormous difficulty if you talk about things being measurements when in fact they are not.
We've poked multiple holes at textbook quantum theory at the Copenhagen Interpretation. This reminds me of a quote by Saul Kripke, who you knew well, who once said that it really is a nice theory. The only defect it has is probably common to all philosophical theories. It's wrong. So what I want to do now is I want to explore a viable alternative. I want to be solutions oriented. So let's talk about an alternative. In 1924, in a paper titled A Tentative Theory of Light Quanta, Louis de Broglie proposed an alternative called pilot wave theory. This is now also known as the de Broglie-Bohm theory or Bohmian mechanics. So let me start with a simple question again. What is pilot wave theory and how is it different from the Copenhagen interpretation?
There's a fundamental difference between the Copenhagen interpretation and Bohmian mechanics. It is this. In Bohmian mechanics, for a system, non-relativistic system of, say, 10 particles, n particles, some number of particles, you take the particles seriously. That's the only difference. Nothing more. Take the particles seriously. Of course, taking them seriously has implications. If you take them seriously, then you take their positions seriously. Since if a particle is anything, it's something that has a position. So take the position seriously. If you take the position seriously, then even if you accept, as you should in quantum mechanics or Bohmian mechanics, that a system of particles has a wave function, that wave function is definitely not the complete description of that system. The most important part of that complete description is left out. You just have the wave function. That most important part will be the positions of the particles. The complete description will consist of the wave function together with the positions of the particles of the system. And what the theory is fundamentally about is how those particles move, the changes of those positions over time. If you leave the positions out, you're leaving out the guts of what's going on. And all you have is the wave function and the myriad mysteries which arrive from leaving out the guts of the description. That's the essence of Bohmian mechanics. Of course, that sort of suggests that the theory Bohmian mechanics has to involve in its equations, dynamical equations, its fundamental equations of motion, more than Schrodinger's equation for the wave function, because there's more than the wave function. There are also the positions of the particles. So you have to have also equations for how the particles move. And you do. And the equation for how the particles move, called the guiding equation, is kind of obvious. If you just know Schrodinger's equation, there's an obvious guess for how the particles should move. In fact, there are basically 10 different approaches about how you might go about making that guess. They all lead to the same equation of motion. So it's really, really obvious. As soon as you, if a very intelligent person with some mathematical ability, given Schrodinger's equation and saying that they're also and believing that they're also particles with positions, and wondering what's the theory, how are these particles actually moving, there's an obvious guess for how they should be moving. That obvious guess is Bohmian mechanics. So for a non-relativistic system in particles, it is in fact the case, given Schrodinger's equation, that Bohmian mechanics involves the obvious ontology, particles with positions, evolving the obvious way. Evolving the obvious way is what I just told you. The equation of motion is just the obvious guess. And why is that the obvious ontology? Well, obviously, if you're talking about a system of particles, then you're talking about particles, things with position. So of course it's the obvious ontology. The very way you speak about the system, a system of particles, tells you what the ontology is. So that's what Bohmian mechanics is, the obvious ontology involving the obvious way.
I see the clear distinction. In Bohmian mechanics, you're treating the particle as something physical. Like you said, you're taking it seriously. And instead of the uncertainty around the position, that position is now determined by a framework, I guess, which is the guiding equation or the guiding wave.
I wouldn't say it like that. It's true, but no, that's putting things in the wrong order.
Okay.
The position is determined by what it is. Particles have positions. So there's not yet. Now the future position is determined from the present position by the guiding equation.
Gotcha.
But that's a step further. That's about dynamics.
Mm-hmm.
What determines the position is the position, because particles have position. There's nothing to determine beyond what you have. Whatever you have, pay attention to what you have in the theory. A wave function and particles with positions. And the extra thing is not the pilot wave. The extra thing is the wave are the positions of the particles. Take them seriously. The wave function is the same wave function as in textbook quantum theory. That's not something added. Although a common mistake made in talking about pilot wave theory is that what many people say, oh, it adds this strange kind of pilot wave. That's exactly what it doesn't add. That's just the thing which was there already in the Copenhagen interpretation and in all versions of quantum mechanics, the wave function. What it adds are the particles. The reason that's hard to appreciate is because it sails under the radar. What do you mean it adds the particles? We were always talking about particles. How can you say you were adding particles? Yes, you were always talking about particles, but you weren't taking them seriously, because if you were taking them seriously, they would have been included in the state description via their positions.
Yeah, I think that's a crucial distinction between the two theories. About one theory, which is the textbook quantum theory, not taking position. There's a lot of uncertainty around the position, whereas in pilot wave theory, you are taking the position seriously. Can you help me?
Let me qualify what you just said a bit. It's not even that there's a lot of uncertainty about the position. If to have uncertainty about the position, there would have to be a position.
Yeah.
So it's a more metaphysical, intrinsic kind of fuzziness and your genuine uncertainty.
Yeah, I agree. Can you help me with the help of the most famous experiment, I guess the double slit experiment? If the position of the particle has been taken seriously, and I guess if there is this fuzziness, has not even uncertainty around the position, if there's a definite position and the future position is being guided by your current state and the guiding equation, how do you explain the results of the double slit experiment? How do you end up seeing that result or that output?
Are you familiar with the picture of the trajectories for the double slit experiment?
I am, yeah.
But we can't show it right here.
I can put it up later.
Okay. So what happens is this. I mean, the particles are guided by the wave function. Therefore, their motion, the structure of the trajectories is affected by the structure of the wave function. When the wave function, which involves a sum of two pieces, a piece coming from the upper slit and a piece coming through the lower slit, when these two pieces start to interfere, so you get an interference pattern in the wave function, that structure in the wave function generates an interference pattern in the pattern of trajectories, so that particles tend to go to certain special places. So conceptually, it's not too surprising that the arrivals of the particles will reflect the structure of the wave function, which after all is guiding the particles. And then if you work it out in detail by looking at the exact equations of motion, you find that you get exactly the predictions of quantum mechanics for the two-slit experiment. And in fact, you also get, by going a step further, the most surprising aspect of the two-slit experiment that Feynman talks about. It's one surprise. But by the less surprising aspect is the fact that a particle which goes through just one slit can somehow, in the orthodox point of view, seem to interfere and behave as if it went through both slits and interfere with itself. But the wave goes through both slits, so that's not a particular problem from the Bohmian point of view. On the other hand, another feature, a really surprising feature that Feynman highlights in his discussion of the two-slit experiment, is that however you are able to measure which slit the particle goes through, this must, as Feynman puts it, must force the particle to behave like a particle and not behave like a wave and not exhibit any interference pattern. As soon as whatever you do to find out what slit the particle went through, however gentle it might be, as soon as it gives you that information, it ipso facto must destroy the interference pattern. And that's pretty striking. And it's perfectly clear, if you think it through, the whole experimental procedure in Bohmian mechanics, why that must be so. I recommend you try to think that through for yourself. It's a good exercise, but it's true. You fully understand all the things that Feynman highlighted as puzzling in the two-slit experiment. They're perfectly clear in Bohmian mechanics. You just have to do the analysis and think things through carefully.
What creates the guiding field or the guiding wave or the guiding equation? What creates the particle? Is this a relevant question to ask? Are we at that stage where we can even start breaking that down even further and seeing what's creating these?
Well, that sounds like a religious question.
I guess I'm asking you whether there's a door open for a creator beyond this, or do you think this theory is just layers above the actual fundamental theory?
No, I mean, if you're trying to understand this theory in its own right, then it's inappropriate to ask, just concerning this theory, what's creating it. It could well be that the theory we're discussing is a tentative theory, not a fundamental theory, that it arises from a deeper level of description. Yeah. Even if the theory is like that, this level of description, this intermediate level, the theory on the intermediate level should be clear what it's saying. Now you could ask, but what kind of deeper theory gives rise to it? And for example, these particles in the theory, are they fundamental, or are there some deeper objects which might constitute the particles? You might call that the creation of the particles. I'm not sure creation is the right word. I mean, the particles are might be made of more fundamental things. Does that mean the more fundamental things are creating the particles? Is that the way you'd like to speak about it? Probably misleading language.
I wasn't planning to go there, but now that it's been brought up, this religious undertone to the question, then I have to ask you about a creator. What does your gut say? Is there like a creator beyond the fundamental theory?
Well, if there is, that's not part of science. So in terms of thinking about physics, I don't think the creator should be brought into the discussion. Now, some people might say, and I guess I'm sure some people have said, that quantum mechanics or the Copenhagen interpretation proves there is a creator. A step in this direction, some people would say, is that measurement creates reality, observation creates reality. And they might go a step further, that God is the ultimate observer of creating reality. Well, respectable physicists have said such things, but certainly such a view is a minority view, very much a minority view. It's hard to do physics by injecting the creator into it. But a more serious question in this direction, much more relevant, is this. One, we may not be sure whether there's a creator or not, but we should be sure that there is such a thing as consciousness. Consciousness is an important aspect of reality. Physics is supposed to explain what we see around us. It's supposed to explain our experiences. But our experiences take place in consciousness. So physics is supposed to explain our experience. As you might say, physics should explain consciousness. And indeed, that's a grand scientific goal, to explain, to account for consciousness, how consciousness arises from the behavior of mere matter. Indeed, in very complex forms, as in a brain, but still the behavior of mere matter. And part of that problem is called the mind-body problem.
Yeah.
And I believe the fact of the matter is that consciousness transcends physics, that physics cannot account for consciousness. So when the statement that physics should explain our experiences has to be taken with a grain of salt. It should explain, we would be inclined to say, everything except consciousness. So that's a serious caveat for the statement that physics should explain all of physical reality. To the extent that you think consciousness is part of physical reality, and you may define it as not part of physical reality, but it's certainly part of reality. Physics it's not going to be able to handle it. At least that's my view.
So if you take this non-physicalist view on the mind-body problem, then where does consciousness reside? If you can't use physical objects to say consciousness is emergent from physical objects, and where is it emergent from?
I don't know. Does anybody know? I think not. I think somebody who has struggled with this question, probably for as far as anybody that I'm aware of, was Thomas Nagel, philosopher Thomas Nagel, in his book Mind and Cosmos.
Yep.
But I think this is this question of consciousness is infinitely harder than the question of quantum reality. And look at all of the controversy and difficulty people have with quantum mechanics, which is not as hard a question, not comparable even to the question of consciousness.
I think this is a fascinating digression, but we could spend hours talking about it. So I'm going to pull us back slightly.
Yeah, we should.
But while we close this loop,
which maybe should be said up front, but then forgotten about.
No, I loved your insights on this. But while we close this loop, we were talking about the creator. I do want to close up this loop. You mentioned that, that's not science and physics, and we won't be able to talk about a creator from a scientific lens. But I wanted to pull back and I ask you just as a human, not as a scientist, not as a physicist, what does your heart say? Is there a creator?
I don't know. Hard to know. My heart doesn't say anything very clear.
Well, let me know. Drop me an email whenever you found out. I'm always curious to know the answer. Okay, let's pull back. We were talking about the pilot wave theory. One thing I definitely want to check with you is that there have been a lot of big names that have been critics of pilot wave theory. When it was presented at the Solvay conference in 1927, Wolfgang Pauli said that this theory doesn't deal with inelastic scattering enough. He was successful in shutting it down and even convincing de Broglie to not pursue the theory even further. Later in life, Pauli called this theory artificial metaphysics. Einstein called the theory too cheap when he saw Bohm's work. Sabine Hossenfelder said pilot wave theory is not able to reproduce the achievements of the Copenhagen interpretation in the standard model.
What? Let's repeat what she said again.
So Sabine has said that pilot wave theory is not able to reproduce the achievements of the Copenhagen interpretation and the standard model. It's not able to reproduce all the results that you've seen from the standard model. David Deutscher has said that pilot wave theories are parallel universe theories in a state of chronic denial. There are so many of these different criticisms of pilot wave theory. So first, I would love it if what you can do is step into the shoes of the critics and maybe steelman the argument. Is there any merit to these criticisms? Are there any open limitations to pilot wave theory that you think have some merit and need to be spoken about?
There are some issues, but I don't think any of the criticisms that you mentioned have the slightest merit.
Okay.
None whatsoever. Because the essence of the theory is to just be clear what you're talking about. There has to be a clear ontology of local beables, things localized in physical space. And any serious version of quantum mechanics, I think, is going to have that. The closest to a legitimate criticism, but it's not really legitimate, I would say, is David Deutsch. David Deutsch's criticism it was viable only to the extent that the many worlds interpretation is viable, which I actually don't believe it really is. But even if the many worlds interpretation were viable, it wouldn't be a legitimate criticism. But now the other criticism, Sabine Hossenfelder's criticism doesn't really make any sense, since Bohmian Mechanics makes the same predictions as orthodox quantum theory. It explains all of textbook quantum theory. In fact, all of the rules in textbook quantum theory, all of them, are theorems in Bohmian Mechanics. So I really don't know what she has in mind. What was Pauli again? Pauli's criticism?
Well, Pauli was one of the first few critics because he shot it down at the Solvay conference.
That was understandable. That he asked a reasonable question. He asked de Broglie to explain what was going on in a certain experimental situation. Yeah. And de Broglie was not thinking well enough on his feet, and he gave a very poor answer. And that shut it down. But in fact, there's a very clear story about what's going on. There's a very clear answer to Pauli's question there. So that's not a serious criticism, not at all. But there was, what about the metaphysical stuff? Artificially contrived? What were some of the others?
Yeah, later in life, Pauli had made a comment about Bohmian Mechanics saying that it's artificial metaphysics. Not sure what you...
Look, if you just... Well, it's easy to see what's wrong with that. All you mean is particles means particles. You're calling that artificial metaphysics? The artificial metaphysics is saying the only thing we have is the wave function. That is a heavily philosophical statement that the wave function is everything. All that Bohmian Mechanics says is that particles means particles. That's not metaphysics. That's saying what your theory is about.
Yeah.
Einstein said it was contrived. Well, I'm not sure how well Einstein appreciated the theory, but I would suspect he might have had in mind something like this. He might have had in mind that he was looking for something rather... He also said it was too cheap, and it is. It's very cheap. It's very easy to convert Schrodinger equation to a sensible physical theory. Very cheap. Maybe Einstein deeply appreciated that, but he wanted to do something much more. Because here's a crucial question. Why should there be any wave function of physical theory at all? Who ordered that, as Robbie asked about something else? Who ordered the wave function? Why should there be this wave function? That's kind of strange. Now, it's not a criticism of the theory, but it's a question you could ask about the theory. Why should it have this object in it? Well, Einstein wanted the wave function and everything in quantum mechanics, including the wave function, to arise from some deeper theory of the kind he writes, some sort of classical type unified field theory. Well, Bohmian mechanics is certainly not that. It just takes Schrodinger's equation, which is in some sense the heart of quantum mechanics, and converts it into a coherent physical theory by saying the obvious. Einstein wanted to do much more. Einstein was much more ambitious.
One alleged criticism, or one alleged comment that you have about pilot wave theories was David Deutsch's comment about the link between the many worlds interpretation. Is there any other open criticism of pilot wave theory that you think has some merit?
There's a technical criticism, which is that there are two technical criticisms. One, a clear, mathematically clear extension to quantum field theory, which deals with it comprehensively, does not exist. Certainly there are various options, and it would be rather striking if it did exist, because even quantum field theory itself is extremely complicated, and you have the whole question of existence of quantum field theories is not so easy. They break down at certain scales. So they're not such clean theories. You have to go through a whole song and dance to make sense of quantum field theories. And then the extension of Bohmian mechanics to relativity is not such a simple matter. Things can be done, but I don't think there's any optimal extension to relativistic theories. However, relativity already gets into tension with what Bell's great achievement, which is showing that if the predictions of quantum mechanics are correct, the laws of physics describing those predictions, whatever they may be, must be non-local.
Yeah.
Non-locality itself is in tension with relativity. And so I would put the difficulty of extending Bohmian mechanics to relativity, which is no reason that it can't be done, but that it can't be done in a terribly clean way, is related to the fact that it's still not that terribly clean resolution of the tension between relativity and quantum non-locality. So the bottom line there is work remains to be done.
Definitely one of the biggest dilemmas of this century has been this merging of quantum theory and relativity, and this theory of everything that will bring them together. And you're saying Bohmian mechanics is also probably struggling to bring them together as well. So it doesn't get us closer to that theory of everything.
Bohmian mechanics for a system of n non-relativistic particles, or a universe of non-relativistic particles, is certainly not the final theory. But there are lessons from Bohmian mechanics. Namely, your final theory, if it be a quantum theory and involves a wave function, should involve more than the wave function. It should involve something which I'd like to call the primitive ontology of the theory, what the theory is fundamentally about. In the case for a non-relativistic system of particles, it's the particles with positions. There could be another different primitive ontology, maybe strings, maybe fields of some kind, whatever. There are all kinds of possibilities for the fundamental ontology of the theory. But there better be such a thing beyond the wave function, I would say. And actually, this deciding on what the most compelling, reasonable choice is may not be such a simple matter as it happens to be for non-relativistic quantum mechanics for a system of particles, where all you have to say is particles means particles. It might not be the case that the answer is so simple for quantum field theory and for other theories, other extensions of quantum mechanics.
That makes sense. As you're approaching the end of the hour, let me just ask you one final big question, and then we can start wrapping up. I have to ask you about why the Copenhagen interpretation, current understanding of quantum theory, gained so much in popularity. I think this could be a great case study in maybe sociology, psychology, how groupthink happens, how cults grow, because I find it very ironic that science, which grew up on the virtue of empiricism and evidence and searching for the truth, often seems to fall into these pits of bias and stubbornness and lacking self-awareness to an extent that theories that it's supporting, they no longer make sense. They become quite incoherent, but still continues to support them Why do you think the Copenhagen interpretation gained so much momentum and popularity when there were so many other alternatives out there as well?
Yeah, I don't know, really. I mean, there are various things that have been written about it. And are you familiar with the quote from Feyerabend about this question?
I'm not.
He talks a little bit. He liked to be controversial, but he wasn't being, to me, terribly controversial here. He noticed that all kinds of weird ideas, like many worlds, but I'm not sure it was just coming on the scene, I believe, many worlds. I'm not sure he had it in mind. He said all kinds of weird ideas flourished, and Bohm's ideas were being ignored. He said he always find it. He said that he hopes that one fine day, historians and philosophers of science will take a close look at the matter. Basically, take a close look at the question you're asking, because it is very hard to understand this history. How did it happen like this? How did people end up saying such really weird things when there was something so simple and obvious that could have been said? This is much harder. This question is much harder than understanding quantum mechanics itself. It's much harder than understanding Bohmian mechanics. And indeed, what I just told you before about Bohmian mechanics, about the equations being so obvious in everything, obvious ontology evolving the obvious way, the natural rational response to that statement is, oh, yeah, that's all fine and good. But if something so obvious were correct, all physicists would have latched onto it. The fact that they haven't proved that theory, that obvious theory you're talking about, can't possibly be right. It makes wrong predictions. That's why nobody talks about it, because it clearly makes wrong predictions. That would be the rational thing to conclude. As it just turns out that all the theories, everything said in textbook quantum theory, except for the bad philosophy, is a theorem of Bohmian mechanics. It does not make those wrong predictions. And that's what's hard to understand. So then why did people not accept the obvious? Well, they really weren't focusing on the obvious for the first 20, 30 years. De Broglie was shot down. Bohm came around, but at that day, Copenhagen was in its heyday, and anybody questioning Copenhagen could have their career truncated, as they tried to do to Bohm. It was really difficult. Bohm had a very tough time accepting and adjusting to how his theory was received. He had huge ambitions about what effect his theory would have. He thought that his theory would make the world safe for communism. Grand political effects. Of course, that seems a bit ridiculous. But he certainly didn't expect it to be utterly misunderstood and rejected. Anyway, that's what happened. Now, and I must say, when I first learned about the theory, I utterly dismissed it because I didn't understand it. And all my teachers had told me that something like that was impossible. And there were the no hidden variable theorems saying it was impossible. And I was inclined to accept all that as a student. It was only a bit later that I realized that was all bunk. Everything I'd been told was wrong. But there's a tendency to believe your teachers, and there's a tendency to believe authorities. That's one point. Second point, Bohr and Heisenberg were much better at public relations than Einstein and Schrodinger, who were critics of Copenhagen interpretation. Einstein and Schrodinger were really concerned about the truth, but they were not concerned with propagating the truth. They were concerned with finding it out. Bohr was concerned with, he thought he had the truth, I suppose, and he was concerned not with a deeper understanding. I guess he thought he had the deepest understanding. He was concerned with winning the public relations war. So the Copenhagen School made a big effort in that direction, and they totally won. There's probably more could be said about that. The early years of the Copenhagen interpretation, the first several decades of the Copenhagen interpretation, until fairly recently, perhaps, were the heyday of logical positivism. First in philosophy, And then after logical positivism was abandoned in philosophy, it was still taken seriously, very seriously by physicists. It was part of their physics upbringing. Only thing that is meaningful is what you can measure. How you measure a quantity defines what it means. All kinds of positivistic statements, which philosophers don't take seriously anymore, and physicists less so because of string theory. But that was part of the what people were spoon-fed in order to get them to accept quantum mechanics. Don't ask these questions because they're meaningless questions, because there's no way you can determine the answer. So they're meaningless. They have no meaning. Forget it. Nonsense, not science. And once you've imbibed that, the more poorly you understand that, the more likely you are to resist abandoning it. And so that was also a contributing factor, I believe.
I do think it would be such a fascinating case study to study how the Copenhagen interpretation gained so much momentum, because we're talking about a theory that has such open questions, so many holes in it. And we're not just talking about, we're talking about some of the greatest minds who were convinced that this is the way forward. And then they imbibed the shut up and calculate phenomenon as well. It's incredible. Like, just on paper, it seems incredulous that this would happen in science, a subject that leads by empiricism, but it did happen. I would love to know like the root causes of it.
So would I. Again, as I said, it's not just that the scientific physics community was more or less almost to a man, but not quite. Einstein and Schrodinger were definitely exceptions, demanding adherence to all of these strange views. But on top of that, there was just sort of an obvious thing to say, which got rid of all the difficulties and all the strange views, the need for all those strange views. Just say particles means particles. So that means that however astonishing it was, it's astonishing squared in view of the obviousness of Bohmian mechanics.
I agree. Would love to know more. Okay, let's start wrapping up. Let's move into some of our closing questions. What are some books, movies, role models that have strongly influenced you in your life?
Well, one thing that strongly influenced me was the book by von Neumann, The Mathematical Foundations of Quantum Mechanics.
Yeah.
Not because von Neumann was advocating anything like Bohmian mechanics, quite the contrary, but still it was an attempt at a very clear formulation of quantum mechanics, which allows you to focus, get a good picture of what the problems might be. There was enough clarity to actually see where there might be difficulties. Things are not obscured by the vagueness. So that was, I found, helpful. And then there were two courses which had a really big impact on me. One by Eugene Wigner at Princeton about, I think, 1975 or so. It was a book on foundations of quantum mechanics, which got written up into lectures on the interpretation of quantum mechanics in the big red book by Wheeler and Zurich, a compilation of a huge number of papers on foundations of quantum mechanics. That book really made it clear to me. That was a great course, the Wigner course, and he had a very nice discussion of the measurement problem. Again, it was not Bohmian or anything like that. And also there were some lectures at Princeton at the similar time by Saul Kripke, which was supposed to be about Wittgenstein following a rule. But when Kripke learned about, just before the lectures were supposed to begin, he learned that some prominent philosophers were advocating quantum logic. This horrified him to the extent that he switched the topic of the course to quantum logic. And Kripke made it extremely clear how idiotic some of the things being said in quantum mechanics were. So I'm sure this had a big effect. What would be the effect? It allowed me to question authority more than I would otherwise have been inclined to do. Another thing which had a big effect on me and bringing me over was the work of another Princeton mathematician, Edward Nelson, who was advocating something in the 1960s called stochastic mechanics, in which the particles are taken seriously, but they move in a fundamentally random way. And Nelson did a lot of work on that. And that kind of opened, and he argued that it gave the same predictions of quantum mechanics. He wasn't entirely clear about that in some respects, however. Nonetheless, it opened my eyes to the possibility that, particles could actually have positions. And we could understand the quantum randomness because there actually is fundamental randomness. These particles are undergoing some kind of fundamental diffusion process. That's where the randomness comes from. So that really opened my eyes and it enabled me to see how one could avoid the conclusions of no hidden variable theorems and understand how the quantum randomness could arise. Could be there because you're dealing with a fundamentally stochastic theory to begin with. It was only a few years later that I realized that all of that was unnecessary and you could arrive at the same thing from a simpler theory, which involves no fundamental randomness at all and just an obvious equations of motion, and that's Bohmian mechanics. But I'm not sure I would have taken the step of actually seeing that the Copenhagen interpretation could be avoided and quantum randomness, and then you could have a much clearer theory involving genuine particles taken seriously without first seeing how that could be done in a fundamentally stochastic theory like stochastic mechanics. Once I was already there, I was able to take the next step and realize you didn't need to even put in that fundamental randomness to get it out. There's also some good books. There's a good book by Travis Norson on foundations of quantum mechanics, and there's some books by Jean Bricmont, which are about foundations of quantum mechanics, which have a very Bohmian slant.
Definitely good introductions to the topic. I'm going to ask you a slightly unfair question. Who do you think is one physicist that had the most impact in history? Who was the most influential physicist, according to you?
In history?
In history.
Wow. Sorry. So, but if I had to say, I would say Newton.
And why?
Because he was the father of modern physics. Modern in a broad sense.
Yeah.
And everything we know takes off from Newton. But I wouldn't trust me on that. I'm not.
Yeah, I agree. It's a slightly redundant question to ask why for Isaac Newton, definitely one of the most influential physicists.
I think we can at least agree that Newton was good.
Yeah, we can reach that middle ground for sure. I also wanted to pick...
The guy who wrote the most clearly about foundations of quantum mechanics was John Stuart Bell.
Shout out to John Bell. The more mention we can give to John Bell, who's also a name that's somehow been snubbed in physics history, but I'm glad it's coming up again. I also have to pick your brain. Just wanted to quickly get your thoughts on Richard Feynman. You had the pleasure of working with him as well. Are there any memories that stand out to you about Richard Feynman? You hear so many stories about him.
Well, I mean, I didn't have much contact with him. I only heard one lecture from Richard Feynman. And he was a substitute teacher at that lecture. Mm-hmm. A great lecture. But Feynman's writing did have a positive effect on me in the sense that he rejected at least some of the positivistic statements associated with the Copenhagen interpretation. He didn't accept everything hook, line, and sinker. And that, again, suggested to me, or sort of gave me a permission structure to question authority. Made clear that some of the stuff being said, Feynman is rejecting it, I can reject it.
Unfortunately, I didn't have the opportunity of interacting with Richard Feynman, but he sounds like such a singular human being, such a remarkable person. Last 3 questions for you. If you could go back in time and give yourself one piece of advice, what would you tell yourself?
With regard to physics?
Or in general?
In general is too hard. One piece of advice. I don't know. I mean, I would like to say, be willing to don't accept. All right, don't accept anything until you can, in some sense, understand it. Don't just take things on authority. And that's a dangerous piece of advice.
Yeah.
Because sometimes you have to be patient. But if something sounds ultimately really too strange, don't accept it unless you can see some good reason to accept it.
So in that spirit, let me ask you, Louis de Broglie had once said that vulnerable like all men to the temptations of arrogance, of which intellectual pride is the worst, the scientist must nevertheless remain sincere and modest, if only because his studies constantly bring home to him that compared with the gigantic aims of science, his own contribution, no matter how important, is only a drop in the ocean of truth. So let me ask you about legacy. How do you want to be remembered after you're gone? What would you like your legacy to be?
I don't actually worry too much about being remembered, but to be honest with you. But what did I do that's significant? I think just tried to understand our most fundamental theory and had some success in that.
When it comes to legacy, is death, mortality, has that ever been a driving force? That time on earth is fleeting, that we have the time we have a shot. Does that motivate you in all the work that you do?
Not very much. Sometimes I would say that maybe I tell myself now, this is something I would like to understand, but really time is limited and I just can't go there.
Perfect segue into the final question. And we had alluded to it earlier. You were talking about the experience of being human. We were talking about consciousness. We inadvertently went into some religious undertones about the creator as well. So let me ask you explicitly as the final question. I've saved the easiest question for the end. What is the meaning of life, Sheldon Goldstein? Is there a meaning?
If there is a meaning of life, it must be entangled in some mysterious way with the nature of consciousness. Beyond that, I cannot say.
What do you mean when it's entangled with the nature of consciousness?
I mean, to the extent that we think of ourselves as special, it's our consciousness which is special. And our ability to think, which is an aspect of consciousness. Computers are said to be able to think, but they don't think the way we think, I suspect. They don't have genuine understanding the way we have genuine understanding. It's genuine understanding and emotion and feeling for others, which is an aspect of consciousness as well, which provides meaning to life. These are the aspects of life that transcend physics and are connected to our nature as conscious beings.
I like it. The subjective experience of being human, the feelings and the emotions it evokes, definitely a great meaning to get behind. Professor, thank you so much. I really appreciate your time. This has been a fantastic conversation. It's been a privilege for me. Thank you so much.
Thank you for inviting me to engage in this conversation. Thank you.